Morning everyone. So we'll start off today with a couple warm-up questions here. Let's see how we do. Remember, anytime you're given a drawing or a structure, you want to see if you can get that UPAC name. If I give you the word name, see if you can get the structure. So this first one, I'm going to ask it slightly differently here. I'm going to give you a condensed formula. So it's just sort of one way they might end up showing this to you here. I would encourage you just to see if you can draw the structural diagram, get a sense of how this is bonded together. But still, at the end of the day, you're just trying to name that compound there. Another molecule here. Let's go maybe an alkene. I'm going to plop some fluorines over here, some H's, all right? And I give you one the other way here. Let's try, say, 3-ethyl, 1,4-dipropyl, cyclo. Hept 1-ine. Okay. As always, I encourage you just to pause the video, give the problems a try, and then when you're done, you can check your work with me here. So assuming you've done that here, let's just go over some of these problems. This first one here, a little bit tricky because it's sort of like a condensed formula. They've still left for you all the carbon parts, but what they've condensed is they've just sort of summarized how many hydrogens are sort of included to each of the carbons. Just to start making sense of this one here, I would just draw the structural diagram first. So a couple hints for us here. We know that if we have a carbon that's on the side of the molecule, because I'm only holding perhaps one other carbon, I do actually have 3 extra arms to actually hold onto hydrogens. So anytime you see CH3, that's sort of a hint that that's sort of a terminal carbon. That's a carbon that's on the side of the molecule. Along the same vein here, if I see the term here CH2 instead, this carbon here is probably not terminal. It's probably not at the side of the molecule. It's probably somewhere mid-chain, so that because I need to hold a carbon on the left and as well another carbon, that only leaves me 2 extra arms to hold on the hydrogens. Now they could very much just say CH2 followed by another CH2. Because they're all CH2 groupings, sometimes they just sort of condense that as well, and they say, okay, we have 2 CH2 groups coming up. So I've drawn one CH2 group, then comes another CH2 group, also not terminal, so it's only holding 2 hydrogens. Then strangely enough here they go to, so I've done the 2 carbons here, then they go on to 1 carbon here, and then they give me here C2H5 2. So let's bond that carbon first. I know that any carbons that are sort of mid-chain are expected to be held 1 carbon on the left and 1 carbon on the right. So that means these 2 other groupings have to be on the side. So maybe they have a C2H5 grouping there. If you like, you can even draw the 2 carbons, and you can just double check for yourself that there actually are 5 hydrogens, which there are. So that includes the 2 that are on the side there. Then you just keep going along here. We see another CH2. So there's a CH2 grouping here. Just try to draw the structural formula just to make sense of this one here. Remember, we're focusing mainly on a carbon backbone. So the carbon is bonded to another C here. Where I might expect to see CH2, you see that we see a CH, we see another Cl. So maybe instead of CH2, maybe one of the arms is a Cl. It doesn't matter if Cl is on top or on the bottom. And then at the very end here, we know this is the side of the molecule again, because we're back to C with 3 H's here. Seeing as I have 3 arms here, I've made it to my terminal carbon there. Okay. So sort of a long-winded way here of drawing out the structure, but once we sort of get that diagram, we do the same sort of things that we're used to, find the longest chain, we name any branches, do the alphabetizing and all that. Even though this molecule here, fairly challenging, we see that the longest chain here is probably the one that's just going to go straight across. So I'm counting 7 carbons here. Okay. When I'm counting the branches here, I'm expecting most of the carbons to be saturated with hydrogens. I'm seeing a couple branches. I have a chloro branch on this end. I have a C2H5 branch and another 2 carbon branch. Those are going to be ethyl branches. Those 2 are actually identical to each other. They happen to be both be on this middle carbon here. And then remember, when I count this parent, I always want to count it so that they're lowest number first. So seeing as my branch here starts off chloro on this side here, maybe I want to count my carbons left to right. Oh, sorry, right to left. We do the alphabetizing here, C for chloro and then E for ethyl. Even though we're going to say diethyl, we still use the E for the ethyl part. So if you can just check your work with me here, I'll probably say this 2-chloro. At position 2, there's a chloro group. At position 4, even though they're both in the same spot, I still need to double the number. So I might say here 4, 4. we say we have a diethyl. So I have 2 ethyl groupings. The ethyl tells you the branch is 2 carbons. The di tells you that there's 2 of these similar branches. They happen to be branched off the same position. I do have to double that number there. And then we just need that parent name. The parent has 7 carbons. I'm looking at the structure. Everything looks like things are single bonded. So I'm back to just saying heptane. Hep for 7, and then A and E for a single bonded family. Moving on to the second one here. This one here is going to be right away an alkene because I see this double bond here. It is between 2 carbon centers here. We know that this one takes priority. We want to make this as small as possible. As small as possible doesn't always mean 1 though. If you find the longest chain, you end up seeing that there's actually 5 carbons strung together. Okay, we definitely want to count it left to right here. Even though counting it the opposite way here, my floral branch would be at 1 and 2. That would make my double bond occur at some later number. I'd rather count it here left to right so that the double bond counts earlier. So we have the counting there. We have 5. Our parent name is going to be pent. Our double bond, the smallest number it could be is stretching between 2 and 3. So pent 2-ene. And then we just need to name these other side fluorine groups here. They're just trying to confuse you a little bit here with hydrogens. I would have predicted most of the other things are saturated with hydrogens anyways. For example, there's H's that are attached to all these carbons. Those aren't new substitutions. So the only substitutions are really where there was a hydrogen. I put on fluorine groups here. There's 2 of them again. So maybe I'll go 4, 5, difluoro, alphabetized for the F in fluoro, but that's the only branch anyways. And then to pent 2-ene. Remember, for alkenes, there's the possibility of having cis and trans. This prefix here goes right at the beginning of the name here. To figure out whether we need cis or trans here, we focus in just on the 2 carbons involved in the double bond. Because the double bond here is rigid and doesn't allow for any twisting or free rotation, we're going to compare what are these carbons holding. So this carbon on the left here is holding a hydrogen. It's holding a 1 carbon chain. Now, I don't normally call that a methyl because that's actually part of the parent, but that's what we're just going to compare for the sake of argument. We have hydrogen, we have a methyl group. On this side here, we have a scary sort of 2 carbon branch off a branch, almost like an ethyl kind of branch. On this side here, we have hydrogen. We notice both carbons are actually holding onto a hydrogen, seeing as those similar groups here are pointed on opposite sides of the double bond. One's pointed up, one's pointed down. This is the cross isomer, so we're going to actually use the terminology. This is the trans form of this isomer here. So if we have cis or trans, you have to include that cis or trans right at the beginning. And there we go, so, trans 4,5-difluoropent-2-ene. That's the full name of that molecule. And last but not least here, as you go to this last molecule, I just threw in an alkyne just for practice here. I usually start right at the end here. The cyclo tells me we're a ring. There's 7 carbons. There's going to be a triple bond. Because we're a ring, we can keep the triple bond starting at position number 1. So let's go carbon, triple bond, carbon. As we start looking a little bit more at the geometry of this here, we're going to see that this part here is actually forced to be straight across. So I have 4 carbons here. Let's just match up a few other carbons here just to form my 7 carbon ring. Because it's up to us how we draw this here, it's sort of up to us how we count it as well. So say I like counting clockwise there. I have 1 through 7. I would imagine that everything else is sort of attached with hydrogens, okay? And then as we just sort of plop this down here, at position 3, we have an ethyl group. So we should have 2 hydrogens there. We have an ethyl group here, which is C and C. We have a propyl group. The propyl by itself would be a 3 carbon branch. One's on position 1, one's on position 4. Let's draw this one here on position 4. I'm already noticing there's going to be a problem here. Okay, maybe you also encountered this when you were doing the practice here. The issue here is you notice this carbon here, because I already have tracked 3 of the unpaired electrons for the triple bond, 1 of them on this side here, this carbon here can't hold yet another carbon chain. That would max out this carbon too much. Okay, so if you drew that here, no problem. I understand why you got that from the name here, but for argument's sake here, that carbon is already saturated. It can't actually hold a propyl group on position number 1. Okay, so sorry about that, but let's see how you did there. Throughout this practice section here, they very often say, oh, what's wrong with this name here? That's something you can try sketching for yourself and you say, oh, that's wrong with this name here. That carbon number 1 here can't actually hold that propyl group. Okay. One extra comment here, just on the geometry of this here. Although Lewis diagrams here, when we just draw these pictures here, they don't really care the geometry, the bond angle, whatnot. We do want to keep track in the back of our mind some of these bond angles if we can. Turns out when we look at alkanes like this first example, alkanes where everything here is single bonded, single bonds, each one of these carbons here hold 4 single bonds. If you remember from our last chapter here, having 4 single bonds means I'm actually a tetrahedral sort of geometry. We get this sort of wedge and dash notation here. You might remember that the bond angle itself, unlike the Lewis diagram where it looks like everything is sort of in rows and nice little columns, everything is 90 degrees. In fact, what we're talking is the bond angle here should always be that 109.5. Single bonds also allow for free rotation. Okay, they twist no problem. Okay, so free rotation. So they don't necessarily have to be along a straight chain like this here. They can actually sort of curve on itself. Let's say the 7 carbon chain. Because the bond angle isn't quite 90 degrees, we can have our 7 carbon chains just sort of kinking back and forth, where the bond angle by itself, all of these angles here are 109.5. That's sort of more like it looks like in real life. I haven't sketched on all these other branches here. And also, because it allows for free rotation, we don't have to be one long snake like that. We could maybe be a snake that sort of have sort of kinked in on itself here. It could wrap in, it can twist in on itself. It can be in any other. We call these different conformers. They're not even isomers. They're just sort of a twisted version of what the molecule is. No bonds have broken. It's not geometric isomer anyways as well. But all these ones here, which we've been pretty easily seeing as 90 degrees, alkanes are actually tetrahedral. They're actually bonded off at 109.5. When we look at the alkene part here happens to have a double bond. This carbon here happens then to have 3 electron domains. For this to have 3 electron domains, so an alkene, if ever I have 3 electron domains, we know the geometry here is actually trigonal planar. Being trigonal planar here, this is 120 degrees. I tried to represent that sort of triangular shape in that geometry there. So not only can we now count, okay, these carbons here have the ability to hold 2 other groups here, possibly giving me cis and trans, we actually are going to be in this triangular flat shape. As we get to the single bond of the alkane part, this part here just sort of starts kinking back and forth. I have 2 carbons here, maybe that carbon there just kinks back and forth. This part will be tetrahedral, this part will be 109.5, that part there will zigzag back and forth, but at least as it pertains to the alkene portion here, that part there should actually just be 120 degrees. Okay. Last but not least, here we have our alkyne. I already alluded to the fact here. The alkyne here as a carbon, triple bond carbon, because these carbons here only hold one other neighbor, looking at this molecule here, if you look at the electron domain geometry, this carbon has 2 electron domains. You tie 2 balloons together, they push really far away from each other here. This is just going to push directly straight across. The bond angle here is actually going to be 180 degrees. So it's going to be a lot wider than the 109 we saw, the 120 that we saw. This part here will actually be straight across. But as we get to, again, the single bonded part here, these other parts here will be 109.5. It didn't really matter in terms of Lewis, right? It doesn't really affect the way we draw it, the way we name it and whatnot. But spatially speaking, we do need to keep track of these bond angles because this does specify a little bit in terms of how reacted these are. Both double bonds and triple bonds here, these ones here, the terminology we use was these are rigid. These ones here do not allow for twisting. That's just the nature of these multiple bonds here. So in the previous case here, because you would need to actually physically break this bond here to actually rotate this side of the molecule here, that gave rise to cis and trans isomerism in this example. So cis or trans. Okay. Later on, you might say E or Z isomers. Okay. Whereas alkynes, albeit it is rigid, because they only hold one single neighbor, there is no, are both of the branches on the same side or the opposite side, they are definitely going to be across from each other anyways. There's no sense of talking cis or trans for that particular isomer. All right. So hopefully you did okay on those practice questions. This whole chapter has been focusing mainly on drawing these ones, doing the naming, and going from there. The last sort of big section that we're going to look at here, we've already started seeing different families. We learned a lot of the rules here with our alkanes. We're going to throw on a few what are referred to as functional groups. Okay. So organic chemistry, it's nice and systematic because these functional groups. Just let me give you a definition for this here. A functional group is a specific grouping It's a specific sort of attachment that these molecules have that have, let's just say, distinctive, special properties, that have special characteristics. And by studying these functional groups here, studying the way these functional groups behave, we can actually have a lot of control over how an organic reaction or organic mechanism actually occurs. Now, these families that we've been talking about before here, let's say if everything happens to be C single bond C, we had called it an alkane family. There really aren't any in particular special functional groups. The functional groups that I have is alkane, just single bond and everything like that. The second that we step over to, let's say, an alkene, start we introducing this double bond here. Yes, the family ending changed. We ended now in ENE. This double bond, when we said it takes priority, this double bond is really special to the molecule. It gives this molecule very specific behaviors. Double bonds are way more reactive than single bonds here because this is a very electron-rich area. It's got like attacking places that are positive, whereas a single bond here doesn't have that same electron density. Okay. Even an alkyne here would be C triple bond C. Okay. Alkyne here even more electron-rich than an alkene. For simplicity, we just dealt with molecules that only had one multiple bond, but that's another example of a special thing, a special grouping, a special characteristic that the molecule has that gives the molecule very particular behavior. So for the next 2-3 lessons or so, we're going to look at a few different functional groups. We're going to need to learn the full naming of these functional groups. And then towards the really end of this chapter here, we're just going to do a survey over maybe 5 or 6 other groups. Those ones there, you just need to recognize what groups those molecules have. We can have a molecule that actually shows off many different functionalities, but we won't need to do a full name for those ones there. Okay. So without further ado here, for today, we're going to introduce the family of alcohols. Drinking alcohol would be an example. This one here is actually ethanol. That's in our beverage alcohols, but it has to be very specially prepared. A lot of these alcohols would make us go blind, so you don't just randomly just drink alcohols just because they're named alcohols. But at least in the organic family here, the functional group that alcohols have, all alcohols contain, we usually say it contains an OH group. Now, if I wanted to just sort of summarize that or give you a little bit more detail of that part there, even though I write this as a OH, the Lewis diagram for that part there means single bond to O, single bond to H. Okay. So a correct Lewis diagram has to have all those lone pairs there. I do have those dots there. The second that I start attaching this new OH group to my alkanes, alkenes, alkynes, and whatnot, suddenly we now belong to the family of alcohols. We now have the functionality of an alcohol. For example, alcohols having this O and H tug of war, this allows for hydrogen bonding. That's a very special characteristic that all alcohols share. Now, you might remember OH from earlier in our course here. We had seen OH before. Let's say NaOH. Let's compare it to just another structural drawing. This guy here is going to be methanol. Okay. One of these is an alcohol and one of these is not. Turns out both of these OH groupings here are pretty much identical. It's O single bond H, the O has 2 lone pairs, everything is identical. The only difference here is, you'll notice in my first example, the Na part represents a metal. The hydroxide would be your polyatomic, in this case is acting like the negative ion here. If I have a metal, non-metal kind of bond, this attachment here is actually an ionic bond. Remember, what happens in an ionic bond is the tug of war is very uneven. The electrons completely get transferred over one way. So what ends up happening is sodium used to have its electron. It gets pulled completely off onto the OH. Sodium is now fully without that electron there. The OH is a polyatomic here. It's stolen an extra electron. It's actually taken on a negative charge there. Remember, for ionic compounds here, they're never so simple as just one single positive, one single negative. They end up forming that sort of repeating pattern, this sort of lattice structure, as we'll say. Right. So even though my Lego block here only needed one Na plus and one OH minus to already counterbalance, we see that the charges are greedy. They surround themselves with as many opposite charges as possible. So in this case here, in the ionic example, we're going to use the name here. That was called hydroxide. IDE as the ending. So that's an ionic compound, that's a lattice. That's not actually an alcohol. It's only an alcohol. If you've noticed throughout this chapter here, we've been focusing on molecules based off of carbon. Well, when carbon bonds to itself here, we're talking non-metal bonds here. We're more often talking about covalent compounds. Not impossible to have ionic, but primarily covalent. So this OH, which is chemically identical to the hydroxide molecule from earlier, this bond here is actually not a ionic bond. It's not a positive negative, it's not a lattice. Covalent compounds are just molecular. They are just the one single blob, the one single grouping. This methanol grouping here, you'll notice I already started naming it. In this case here, we do call it an alcohol family. Now again, usually if I have a special grouping, if I have a different family name here, we look at the ending of the name here. Alcohol ends off with OL. So we have an alcohol that starts off just with one carbon. If I give you the name of this one here, methanol, well, we know the meth part. The meth stands for one carbon, right? We had done it for methane, in this case here, methanol and other functionalities. But you notice the ending here, we do end it off with OL to remind ourselves this one here is actually the alcohol version of it. Just to distinguish the fact, hydroxide was for ionic. This one here, we often just call it a hydroxyl group. Sometimes you might even call it a hydroxyl branch sometimes, okay? Hydroxyl just indicates, yep, we're in the alcohol family, changes the ending. That's the special functionality that all alcohol families have, okay? So we are looking just down this sort of covalent family here. Let's do a few other molecules. So let's say we have 2 carbons. Pretty much here, let's say we would have been ethane. Everything's all single bonded. Just like we've been doing with our substituents here, let's imagine removing what would have been hydrogen, and let's sub on a hydroxyl group. So we now have the alcohol that has 2 carbons. We can do the prefix here. Well, prefix for 2 is going to be eth. Again, just like with our alkenes, alkynes, this OH group here takes priority. That group here is more important to the molecule than the rest of the alkane part. So if I can, I'm going to choose to put the OH group as the smallest number possible. So I'm going to count it 1 and a 2 here. So we have ethane, okay? You could technically call it ethane 1-ol like that, okay? So we have an alcohol functionality, an OH group that starts on position number 1, just like a branch. But for a really short alkane like that here, whether I put the OH on the right-hand side or the left-hand side here, I would just renumber this as number 1. That is only the only place it could show up anyways. Chemists are usually lazy. They usually drop that 1 there. Not wrong of you to leave that 1 there, but we definitely want to have that as the smallest number and indicate where it actually shows up. Okay. Let's try a slightly longer molecule here, draw you a different diagram. Let's say I have 4 carbons, string like that. Let's say I plop on an OH. Let's compare this again against another 4 carbon chain here, and let's plop the OH down on the side here. Okay. Same idea. They give you the molecule. They want just the drawing of this one. Okay. So when we find our parent, we're going to look at the longest carbon chain. Usually I just circle the carbon chain. We are a 4 carbon chain in both of these. So both of these are going to be examples of butane. Now because I see the OH functionality, I'm going to change the ending to OL. Just like any other branches I might see, my branch needs to be at the smallest possible position. Let's count it left to right. So this actually occurs at number 1. So you could totally call it butane 1-ol. Sometimes they put the 1 in front, okay, just to tell you where the alcohol grouping, that special grouping, shows up. Let's compare it against this skeletal structure on the right-hand side. Remember, it's understood every kink there is going to be a corner. We see that this OH group here is sort of mid-chain. We actually want to count it right to left, so my alcohol actually occurs at a smaller number here. Smaller number here is going to be 2. You can call it 2-butanol as well, just to give you some variety here. You can call it butane 2-ol like that. They have a different name, so they're a different molecule. If you look at the general formula of this one here, though, they all happen to be the same formula. They would have had a C4. The alkane by itself would have been H10, right? I go 2N plus 2. It's just that for one of these H positions, I replaced the H and I actually subbed on an OH. So what we usually do is we broke off a branch, let's make it H9, and we usually still write it OH like that. Now I know this hydrogen is identical to this hydrogen there, but rather than say C4H10O, where I'm not so sure that 9 of the hydrogens here are the normal hydrogens that we're used to, and 1 of the hydrogens are actually extended to the O, usually I leave that H here with the O to recognize that that's an alcohol grouping. So we probably don't summarize it into that condensed molecular formula there. This guy here actually happens to have the same molecular formula. What is it called when we have two things having the same numbers of elements but different names? We saw this type of isomer here. We're not just going to randomly just sort of kink this along, move this along and whatnot. It has to happen by chemical reaction. I need to physically break this bond, physically reattach it. These two here are actually referred to as structural isomers. We were back about a week ago when we started looking at these structural isomers. We started asking, well, where are all the possible places that this branch could show up? These are example structural isomers. Even though they happen to have the same formula, they are actually different molecules. Okay? The one other thing that I'm sort of introducing here in this example, alcohols can also be categorized as primary, secondary, or tertiary. We only focus in on the carbon that's holding the alcohol grouping. So the carbon on the left here, carbon number 2 here. One easy way to recognize whether we're a primary, secondary, or tertiary alcohol, we look at what else is attached to this carbon here. My special carbon that's holding the hydroxyl, that's holding the alcohol group, you'll notice it's only holding one other carbon. The other two are just saturated with hydrogens. This carbon here, we're going to refer to as a primary carbon or primary alcohol because it's only holding one other carbon. Let's compare it to this other right-hand molecule here. This carbon, if you just see its 4 attachments here, it's holding one carbon, in addition to the functional group. What else is it holding? Should be able to draw that it's actually holding an extra hydrogen. Because it's actually holding 2 carbons already, we're going to call this one here a secondary carbon, or in this case here, a secondary alcohol. All right? So primary, secondary, this does come into play when we look at reactions. Primary alcohols can be oxidized in a different way than secondary alcohols, but that's a good way of just tracking different classes of alcohols just based off how many other carbons they have. Okay. Let's just do one last molecule here. Let me draw a little bit larger diagram for you. OH, F, C2H5, and sure, we'll just leave it at that there. Okay. So just like before, given a structure like that, see if you can give me a sense of the word name. Okay. Be careful when you're looking for the longest carbon chain. Very often it is, well, the one I draw first, okay? But you do want to just start from any side to any side. You'll notice this one here that I've condensed on you. This part here that looks like an ethyl group, that part there is actually a carbon bonded to yet another carbon there. So if you sketch out that carbon there, actually having the chain kink upwards is actually a longer chain than just going to the side here. Okay. So if that's my parent here includes 1, 2, 3, 4, 5, 6, 7. So our parent, the last word in the name is going to be hep something. We're all single bonded, so no alkenes, no alkynes. So this is going to be, would have been a heptane, but I do notice that there's the alcohol functionality. This is the special grouping that gives this molecule very particular behavior. This group here takes priority, so this group has to be the smallest number. You'll notice if I count it left to right, 1, 2, 3, 4, 5, 6, 7. My other branches are at 4 and 5. If I count it the other way here, where these branches here could have been smaller numbers 3 and 4, that would then make the hydroxyl group too high. So I do count it. So the OH group here comes at the smallest number. We can say heptane 2O or 2-heptanol if you like. And then the rest of the branching we've done before. This one here is a methyl branch on position 5. This is a fluoro branch. We alphabetize those there. So let's go 4-fluoro. And then we have 5-methyl. All that part there is what we're used to. Okay. So what we've learned today, the OH group puts us in the alcohol family. The alcohol family changes the final ending to OL. Okay. There are times that I'm going to have a molecule later on that has both OH as well as other special groups. In that case there, when I have multiple functional groups here trying to fight for priority, the OH is actually fairly low priority in comparison to other functional groups. So every now and then, not exactly in this molecule, every now and then you might even refer to OH like a branch like the FNCl, the CH3 grouping here. This OH here, we might sometimes see it later on as 2-hydroxy, where hydroxy actually represents that OH branch. In this case here, because OH was the only functionality here, we kept it as the suffix, the family name, but later on when we start introducing multiple functional groups here on the same molecule, we could label this branch here as actually a hydroxy branch. I know the group is called hydroxyl, but just to give it a little bit of difference between an alkyl group which ends in YL, we're just going to say hydroxy as the ending for the OH. So if I happen to have maybe 2 OH groups, it could be a dihydroxy grouping. Okay. So your practice sheet here will have a few alcohols for you to go through, look through some structures, get the word name, look through some word names, see if you can draw the structure. Thanks, guys.